the service I received is already realized very long distance transmission. So at this time, this input port we want sensitive must be very good. But after we amplify the service will send to the local station to demultiplex it. So again, no need a very good. Just maybe 20 dB is enough for me, right? But for the line amplifier, it should receive the service from long distance transmission, and it will send out to realize another long distance transmission. So for this amplifier, the sensitive should be very good, and the gain also very good, right? So that's three different places for EDFA, and you have different requirements in three different places. Okay, that's the amplifier. Okay, we are finished about the amplifier. Let's see another very important technology, that is multiplexer and demultiplexer.
Okay, so before we use the multiplexer, demultiplexer in WDM system, actually we also have some requirement like other technology of WDM, of multiplexer and demultiplexer. The first one is we want the number of multiplex data channels is sufficient. The insertion loss is low, and the crosstalk attenuation is large, and the passband range is wide. So that's what we want for the multiplexer and demultiplexer. Theoretical, a multiplexer is the same as demultiplexer. There are only different lines in the direction of input and output optical signals. Okay, so you check actually just a different direction. You know, our optical signal can transmit in both bidirectional. Okay, so with those requirements, we find two different technologies can be used, which is TFF, thin film filter, and AWG. It's two different technologies can be used in our WDM system. So what is TFF? What is AWG? Let's introduce them one by one. So TFF. Okay, so this is our TFF. TFF comprises tens of alternating layers of high and low reflective index thin films, which are made of different materials and have varying thickness. The thickness of each thin film is a quarter of wavelength. Okay, so that kind of feature will make our TFF can allow the passband transmission of required wavelengths, but blocks those unwanted wavelengths through a stop band. So check this out. When you have a lot of wavelengths input to this TFF unit, then because this part, the materials is special, such that only emit one wavelength, lambda 1, being reflect output, okay, and other wavelengths will be reflect, okay, reflect, and at this point only lambda 2 be reflect, other wavelengths reflect. So at this time we can demultiplex the wavelengths one by one. But check this procedure, you will know the first wavelengths only pass through this kind of routers, but the last wavelengths be demultiplexer will be pass through this kind of routers. Okay, so you will find out the attenuation for different wavelengths will be different. So if you have a lot of wavelengths needed to be demultiplexing, such as 80 or 40, so you can see the last wavelengths will pass through too long in this unit, so attenuation will be very high, so maybe the power will be too low to demultiplex it from the main path, right? So actually TFF can only used for less than 16 wavelengths network. So if you have more than 16 wavelengths, this TFF cannot use for it. So because these features, TFF are widely used in CWDM system. We are in DWDM system, we also use it, but only for some small stations, access layer, which can only need a few wavelengths, no need too much wavelengths to configure. Okay, so that is the feature and the principle about the TFF. Let's continue with our AWG. Okay, AWG means arrayed wavelength grading. That is a planar wavelength device developed based on optical integration technology. Typically, an AWG is fabricated by depositing a glass on the silicon chip and printed into required pattern using photolithography. So for AWG, we can multiplexer and demultiplexer a lot of wavelengths at the same time. Different wavelengths will have same routers in this unit, so AWG can use more than 16 wavelengths. So for DWDM system, we use AWG a lot. So if you are interested in it, so when you guys learn the hardware, you will see AWG in our multiplexer demultiplexer in WDM system. It's very suitable for ultra high speed and large capacity WDM system. Okay, so that's the advantage of AWG. Okay.
Okay, the next technology is our supervisory technology. Actually, for supervisory technology, we have two different ways, optical and electrical. The OSC is use a special wavelength to carry our supervisory channel. Okay, so which wavelength we should use and which kind of supervisory channel we should carry. Before we know that, we have some requirement on optical supervisory channel. You can see the first one, the bumping optical wavelengths on OA board should not be repeated at our supervisory channels. Because our Roman amplifier use the bumping source is 4080 nanometers, so it cannot be repeated. If we repeat it, the OSC channel will be down, right? And the second one, service of the future 3010 wavelengths should not be used. So you can see, if we are using 3010 nanometers to carry OSC channels, maybe in the future when we discover some new amplifier, we can amplify the service in 3010. So maybe we need to replace the wavelengths for OSC. That will waste the money and waste the time. So we don't want to use the 3010. Okay. And the third one, the OSC is still varied when the OA board fails. So we must keep the supervisory channel is working when the optical amplifier board is broken. So how do we realize it? The solution we use is OSC channel never pass through the OA board. The OSC channel never pass through the OA board. When we arrive the OA board, we will demultiplex the OSC channel in from the main path. Then the service will go to be amplifier. Okay. In the south station, after the service being amplifier, we use the special board multiplex the OSC channel into the main path to transmit it. Okay. In the same station, we use before the service be amplifier. In the station, we use a special board to demultiplex the service, the OSC from the main path, and then give the service to amplifier. Right. So that's why in the OSC application, we have one special word, this FRU. FRU. The FRU is used to multiplex the OSC channel into main path and demultiplex the OSC channel from main path because this requirement. Okay, so the last request is the OSC supports ultra-long haul transmission and provide the function of session-specific bidirectional transmission. Okay, for this kind of request, we produce a very good OSC board. For this kind of board, the sensitivity of this OSC board is very good. The receiver sensitivity of OSC can reach the minus 48 dBm. That means after long distance transmission, the power is already decreased too much until minus 48 dB. We can still got the OSC signals from this very low power. So that can make our OSC can support very long haul transmission. Okay. After meet all of those requirements, so we are using 5010 nanometers for OSC, and the transmitter bandwidth is 2 megabit per second for OSC. Okay, and the hardware we used is OSC board, FRU board in our WDM network. You can check. The OSC board can launch 50 nanometers, then send it to FRU. FRU multiplex into main path to transmit long distance. After it arrives at the sync station, the FRU in the sync station will demultiplex it from main path, send it to OSC. OSC will analyze it like this way. Because the bandwidth is 2 megabit, which kind of information we carried by the OSC channel? You can see the OSN frame structures. Okay, the OSN frame has 32 bytes. 32 bytes. The first byte T0 is frame alignment. frame. It's used the height of this frame. So after we detect this alignment frame, we know this is height. So we can detect other frame one by one. Okay. So TS1 and TS19 is E1 and E2 byte. E1 and E2 byte are auto wire phone overhead. We use this byte to transmit the phone signals between two stations. So you can make a phone call between two stations carried by this overhead. Okay, and TS2, TS18, and TS17 are F1, F2, F3. They are transparent transmission of data in the same direction. Those overhead didn't be used now, so maybe it will for some other functions in the future. Okay, TS14, which is ALC, is short for AOC is short for automatic level control, is the automatic power commissioning functions. So it should carry some protocols to each station. After you deploy this function, you need the OSC to carry this kind of head. Okay, and TS3 to TS13 and TS15 is very important overhead. They are D1 to D12 DCC bytes. DCC bytes is used to carry the communication protocol between two stations. Huawei equipment use Huawei ECC communication protocol, so they are carried by D1 to D12. If this kind of byte is broken, so the communication between two stations will be down. So it will affect your communication between two stations. So that's the frame in our OSC. Okay, and we have another solution that is ESC solution. ESC solution, you can check the features. This one is simple structure and low cost. Why is simple structure low cost? ESC means electrical supervisory channel. Okay, we put all the supervisory channel at E1 to D12, like E1, E2. We put into the overhead and add it into our service signals by OTU board. Okay, because OTU will convert the service from optical to electrical. In the electrical layer, you can add the overhead, you can align the overhead, you can configure overhead, right? So we add all the supervisory channel into your service by OTU board. Okay, so we don't need extra OSC board over here. We don't need extra FIU board over here. So make you simple and structure and low cost, right? And then we have backup. Between two stations, you have a lot of different wavelengths. So our ESC can carry by any OTU by any wavelengths. Okay, and also without two FIU between two stations, FIU also has insertion loss. One FIU almost has 1 dB insertion loss. So without two FIU, so 2 dB will be saved over here. Okay, so the optical power will be much better. Okay, and it will be reduced O&M complexity. But also the ESC has one big disadvantage, that is it cannot use to monitoring the OA station. Okay, because if you want to detect the ESC, you must convert the signals from optical to electrical. But our optical amplifier can amplify all the service in optical layer without convert the service from optical to electrical, from electrical to optical, like this process, right? So at this time, the ESC cannot be analyzed in all amplifier stations. So the amplifier station cannot be monitored by ESC. That is the disadvantage of ESC. Okay, so we have two questions for these chapters. The question one, the mechanism for EA modulation lasers.
I think his answer will be very clear. The EA modulation does not directly modulate the light source. In this modulation method, an external modulator is used on the output path of the light source to modulate the light wave. This modulator is equivalent to a switch. Okay. The second question, what is the difference between an EDFA and RFA? I think after we learn the amplifier, this will be very clear. EDFA, RFA has a lot of difference. For example, EDFA can only amplify 50-50. Raman amplifier can amplify any wavelengths. EDFA, the gain is good. Raman amplifier gain is not good. The EDFA has more noise than RFA. The EDFA do not need too much energy to make it working. The ROM amplifier need a lot of energy because we have a very high power bumping source, right? So you can see we have a lot of difference between these two amplifiers. Okay, so that's everything about this chapter. Thank you for your listening, guys.